Hello and welcome to this short clip which goes through a simple chemical reaction from an A-level perspective. It may well be that your teacher has demonstrated this in the lab, and what I'm going to do is do my demonstration of it, but I've filmed it up close, and afterwards I'll put forward some questions that are based on fundamental A-level chemistry ideas for you to think about, either by yourself or with a friend, so you can try them on a paper or a whiteboard and see if we agree when I go through the answers. So the first part of the clip will be about checking any safety notes I'm given in my instructions and the hazard symbols for my reagents. So I'll sort of point at them as I show them. So the first question is an atoms, ions and compounds question. It gives you some information. Aluminium forms 3 plus ions, whilst I2 forms 2 I minus ions. It asks you to construct a formula for aluminium iodide and use this formula to construct a balanced equation for the reaction between aluminium metal and solid iodine. So the first thing to do is to write out the ions that you're given. I'd ask you to now pause the clip and see if you can put forward an answer for this. And resume playing when you've come up with something. So you multiply each ion by the charge of the other to get the lowest common ratio for a neutral compound. So that means aluminium gets multiplied by 1 because of iodine being 1 minus, and iodine gets multiplied by 3 because of aluminium being 3 plus. So that now gives us AlI3. So now what we have to do is to construct an equation for how that's created. So although this isn't balanced, I've added the state symbols because it's told me to add the state symbols, and it's said aluminium metal and solid iodine, and we know that the aluminium iodide is a solid because we've seen it in the clip. You'll notice I've left some spaces in front of all of the reagents and products because I want to work out my balancing numbers. So where do I start? Well, aluminium seems to be balanced at this particular point in time, but iodine obviously isn't. There's 3 iodines on the right hand side, 2 iodines on the left hand side. What's the lowest common multiple of 2 and 3? So that's obviously 6. So you need 6 iodines on both sides. So now what we can do is balance for aluminium. Because we know we have 2 aluminiums on the right hand side, because we need 2 AlI3s, that must mean that 2 goes on the left hand side as well. So that gives us our balanced equation. So the next question needs you to have a little bit of familiarity with moles and masses. By this stage I'm assuming you've done some work, perhaps as independent study or in class. So for this you'll need a little formula, moles equals mass over molar mass, to help you. So we start out with the data. So once you've identified your data, you lay it out nice and neatly, even put data next to it to help you in the first few times you try this. Now you can try out the moles. So what we do here is we use the equation for moles and mass. So using the equation moles equals mass in grams over molar mass in grams per mole to the minus 1. For each of my reactants I've taken its mass and divided it by the appropriate molar mass. And I've taken the values exactly from the periodic table, except for one of them. You can see that I took the relative atomic mass of iodine as 127 and multiplied it by 2 because I'm dealing with I2 in the equation, which I've now highlighted in the equation in red at the top. So this is something to watch out for in equations. Don't just transfer over the atomic mass from the periodic table. See if you have to multiply it up first. So the next thing to do is to check the equation. And the balanced equation tells us that the ratio in which aluminium and iodine react with each other is 2 to 3. So this bit's a little bit harder. You've got to use the equation's mole ratio, that 3 to 2, to work out the exact amount in moles required by each reactant. So what you need to ask yourself in each case is how much of the other reactant do I need? So how much aluminium does 0.00788 moles of I2 react with completely? And vice versa, how much iodine does 0.0185 moles of aluminium react with completely? Once you've realised what you're asking, what you're trying to work out, you can simply apply the mole ratio across and it becomes very straightforward. So what we've just done now is applied the mole ratio for the equation to the amounts of each reactant that we've got. So we know how much iodine we need to react with our amount of aluminium, and we know how much aluminium we need to react with our amount of iodine. The question is, which one is in excess and which one is used up first? So I'm going to get rid of the instructions on the right hand side, the black writing, and I'm going to try and take you through it. So the amounts reacted are in brown. So we were able to use our calculation earlier to arrive at this point where we know how much each of our samples of reactants require in terms of moles of the other reactant. So now we know how much each one requires, let's see how much is available. So for our aluminium, for the iodine, left-hand side, we have 0.0185 moles of aluminium available. That's more than we actually need. So by difference, I'm able to work out that my aluminium is in excess. So applying the same idea across, by difference we can work out that we are 0.01987 moles of iodine short of what we need. So the iodine is used up first. It's a limiting reagent, so the reaction will stop after this. And the mass of aluminium left, i.e. how much the other one was in excess, is moles times molar mass. I'm rearranging the equation in the box, and that gives me 0.03247, which is the moles that were left over. And you multiply that by the molar mass in grams, which is 27, it gives you 0.357669 grams of aluminium. Okay, so these two questions were fairly challenging. Well, the first one maybe not, the second one most definitely. It's a toughie. But I thought I'd just give you a little bit of a perspective on an A-level demonstration, the various things you can pull out of it. There's lots of other questions you could ask about that particular reaction. You could go into moles more deeply, you could go into electrons, bonding, structure, all sorts of things. Okay, so let's try one more question that you might be able to attempt. This one is going to be on bonding and structure. So the next thing to think about is the bonding and structure within this compound. So if we start with the melting point, which is a property of a compound, the melting point of aluminium iodide is 189.4 degrees C, which is actually much lower than an average ionic compound's melting point. This can be explained by the bonding being actually covalent, which is itself quite unusual. It's not what you'd expect for a metal combining with a non-metal, and certainly not what you would have been taught at GCSE. To think about this, the question asks you to draw a dot-cross diagram to show the likely covalent bonding in a molecule of AlI3, and then use your dot-cross diagram to suggest why aluminium actually bonds covalently in many of its compounds. So you need to pause the clip and grab a scrap of paper or a whiteboard and give this a go. You may want to have a chat to the person next to you if you're doing this in class, or if you're doing it at home or in college, perhaps in your own time, you might want to pair up with a friend and have a think about it together. But when you think you've got an answer, you can start the clip again. So it's a good idea to start off by allowing plenty of overlap between the shells of your bonding atoms, because this place is where the bonding electron pairs will go. So once you've put in the bonding pairs, you've dealt with having the covalent bonds in your diagram. It doesn't really matter whether aluminium has the dots or aluminium has the crosses. What you've now got to do is decide. So my iodine atoms don't have all their electrons in place, obviously. Aluminium does because it's in group 3, so it's got either 3 dots or 3 crosses. It doesn't really matter, like we just said. But the iodine's remaining electrons need to be in pairs. We call these lone pairs in chemistry because they're not bonded. So I'm going to go with iodine being dots. So now I do a quick check. Do all my atoms have their own electrons to start with? That means aluminium has to start with 3, and iodine has to start with 7. So looking at the dots, that's the iodine. Each iodine has 7 electrons. And looking at the crosses, the aluminium has 3 electrons. So that's done. Do all the atoms have 8 electrons as a result of covalent bonding? Well, looking at the iodine, yes they do, but the aluminium doesn't. So aluminium only has 6 electrons. So what's going on? So the simple answer to this is that aluminium bonds covalently in many of its reactions because 3 electrons are too many to lose all at once. You probably remember that metals lose electrons in most cases when they react. But aluminium isn't able to do that because that's a lot of electrons to take away all at once. Neither is it able to take further 5 electrons itself to complete its octet of 8 from another element. That also requires quite a lot of energy, which aluminium might not have. So it's left having to compromise. So, as is quite often the case at chemistry at A level and beyond, the actual answer is a little bit more complex, which involves factors such as shielding of the outer shell electrons or electronegativity. These are ideas that are covered in the A-level course, and if you're watching this as maybe a second-year student or a first-year student towards the end of their first year, you'll probably be able to go into these a little bit more. If you're watching it as a student at the beginning of your course, don't worry just yet because these will be covered during the first year of your course. But it does give you some things to go and think about. So hopefully what this clip has done is take a relatively simple reaction and show you all the different ideas from A-level that you can apply to it and make you think a little bit about extending some of the GCSE ideas that you would have picked up in year 10 or year 11. Okay, so in the meantime, thank you very much for listening and thanks for your patience in giving it a go. And until next time, see you soon.